Right now, somewhere in Texas, an AI is answering 311 city service calls. No human involved. In the UK, a major police force is preparing to let an AI handle non-emergency calls starting in 2026. And inside the United States Internal Revenue Service, an AI agent is already handling legal queries. These aren't chatbots. They're something fundamentally different. Something that can act on the world. And the wild part? Most people, even the people building with them, can't fully explain how they work. So let's fix that. This is how AI agents actually work. Before we go any further, here's something worth sitting with. The entire premise of AI agents comes down to one formula, so simple, it almost sounds like a trick. And once you hear it, the rest of this video is going to make a lot more sense. An AI chatbot is passive. You type something in, it responds. One prompt in, one answer out, and it forgets everything the moment you close the tab. It has no memory of you, no ability to act, no way to reach beyond the conversation window. It just responds. An AI agent is something completely different. The formula is almost insultingly simple. Take a large language model, give it tools, and give it a goal. That's it. 3 ingredients. But that combination changes everything. While a chatbot responds, an agent acts. It can search the web, write and execute code, send emails, book reservations, fill out forms, navigate your computer, all on its own, step after step after step, without you prompting each move. The agent decides what to do next. It decides when the task is done. The market data tells you how fast this shift is happening. A survey of over 1,000 business decision makers found that 57% of companies already have AI agents running in production. A separate survey of senior executives found 79% of organizations say AI agents are already being adopted at their company, and analysts project that by 2027, half of all enterprises using AI will have launched agentic pilots. Something is happening here, something bigger than the chatbot era. But to understand it, you need to understand what's actually running underneath. You need to understand the loop. Here's something that will change how you see every AI demo you've ever watched. Every single agent, from a simple travel booking assistant to a complex research system managing dozens of tasks, runs on one fundamental engine. It has a name, and once you see it, you cannot unsee it. The engine is called the React Loop. That stands for reasoning and acting. It was introduced in a research paper in 2022, and it has since become the backbone of nearly every production agent system in existence. Here's exactly how it works. The agent receives a goal. It thinks, generating an internal chain of reasoning the user never sees. Based on that reasoning, it decides on an action. Maybe it calls a search tool. Maybe it runs a piece of code. Maybe it reads a file. It executes that action and observes what came back. Then it loops. It thinks about what it just learned, decides what to do next, acts again, observes again, and it keeps looping until it decides the job is done or until something breaks. In production code, this looks almost mechanical. Prepare context, call the model. If the model wants to use a tool, run the tool, add the result back to the context. Loop again. If the model produces a final answer, stop. That's it. That's the engine inside every agent. Researchers have documented agent runs taking tens, sometimes hundreds of passes through this loop before completing a complex task. The loop is the agent's entire cognitive existence. But here's where it gets interesting and alarming. Because there's something the agent uses to think inside that loop that is physically limited. Something that can quietly degrade and cause failures in ways engineers didn't see coming. It's called the context window. Imagine you're trying to solve a complex mystery, but every time you sit down to work on it, someone has erased part of your whiteboard. You can still function, but what you can see right now, actively reason about, use to make decisions, is limited by the size of that whiteboard. That whiteboard is the context window. It's the maximum amount of text a large language model can see and reason about at any single moment, measured in units called tokens, roughly 3/4 of a word each. When ChatGPT launched in late 2022, that whiteboard was 4,000 tokens, about 3,000 words. By 2025, the numbers had exploded. GPT 4.1 supports 1 million tokens. Meta's Llama 4 reached 10 million tokens. The whiteboard got enormous. But here's what researchers discovered when they started stress testing these massive context windows. Performance doesn't stay stable as you fill them up. A landmark 2025 study measured 18 different models, including GPT-4, Claude, and Gemini, and found that accuracy degrades in surprising and non-uniform ways as context grows longer. One striking finding, GPT-4's accuracy on certain retrieval tasks fell from 98.1% to 64.1%, based purely on how information was positioned inside the window. Not what the information was, just where it sat in the pile. The more the model had to sift through, the more likely it became to lose track of critical details buried in the middle. Researchers gave this a name: context rot. More damning for production engineers. Real usage data from agents built at scale found that agents consume roughly 100 tokens of input for every single token they generate. 100 to 1. Every token costs money. Every token affects accuracy. The context window is not just a memory limit. It is the dominant cost driver, the number one architectural constraint, and as we'll see in a moment, the primary security surface of every serious agent system. So if the context window resets, how does an agent remember anything? How does it know, weeks later, that you prefer morning meetings, or that your company's coding standard uses tabs, not spaces? This requires a completely different architecture, one that lives entirely outside the model. An LLM without persistent memory is like a brilliant colleague with severe amnesia. Genius level smart. But every morning they walk in having forgotten everything. Solving that problem is one of the most active frontiers in AI engineering right now. Agent memory comes in 4 forms. Working memory, that's the context window. Everything visible right now gone when the session ends. Episodic memory, specific past events, like knowing that last Tuesday you asked the agent to reschedule the board meeting. Semantic memory, general knowledge and preferences, like knowing your preferred coding language is Python. And procedural memory, knowing how to do things, storing successful workflows the agent has run before. The technical architecture works in layers. Raw data, documents, emails, conversation logs get stored in what are called vector databases. These don't search by exact keywords. They search by meaning. They store content as numerical representations that let you find relevant information even when the exact words don't match. That stored data gets structured into memory objects, user profiles, project histories, preference summaries. And at runtime, the most relevant fragments get retrieved and loaded into the active context window just before the agent needs them. This technique, pulling external knowledge into the model's live window when relevant, is called Retrieval Augmented Generation, RAG for short. And it's what allows agents to feel like they know you even when the underlying model has no persistent state. Memory gives an agent knowledge across time, but tools give it power across the world. And connecting to your calendar, your files, the internet, your database, all of that required solving a problem that was quietly strangling the entire agentic ecosystem, until a single protocol changed everything. Here's a thought experiment. What's the fastest way to research, write, fact-check, and format a 50-page technical report? One person doing it all sequentially, or a team of specialists working in parallel? The answer seems obvious for humans. It turns out to be exactly the same logic for AI. A single agent has one context window, one thread of reasoning, one point of failure. Multi-agent systems break complex tasks into components and assign each to a specialist. One agent searches the web, another analyzes data, a third writes, a fourth reviews for errors, a coordinator agent manages them all, a manager AI overseeing worker AIS. Anthropic published the most concrete data on this in 2025. Their multi-agent research system outperforms single-agent runs on 90.2% of evaluation tasks. The trade-off? Multi-agent systems use approximately 15 times more tokens than single-agent interactions, so they're economically justified only for high-value, complex work. But the performance advantage, when used appropriately, is significant enough that 66% of production AI implementations now use multi-agent designs rather than single-agent approaches. The coordination patterns vary. In a sequential workflow, Agent A hands off to Agent B, who hands off to Agent C. In a parallel workflow, multiple agents work simultaneously, and a coordinator synthesizes the results. In a hierarchical workflow, an orchestrator manages specialized workers like a project manager running a team. Each pattern has trade-offs in cost, speed, and complexity. But all of these agents, single or multi, need to connect to tools and data sources. And before late 2024, doing that required custom integration code for every single connection. It was like having a different charger for every single device you owned. Then one release changed the game. In November 2024, Anthropic released something called the Model Context Protocol, MCP for short. Developers immediately started calling it the USB-C of AI. MCP is a universal open standard that lets any large language model connect to external tools, databases, and APIs through one standardized interface. Before MCP, if you wanted your agent to query a database, send a Slack message, search the web, and read a PDF, you needed 4 separate custom code bases. With MCP, all 4 connect through one protocol. The agent simply calls a tool by name, passes structured arguments, and receives a result. This is called tool calling, and it's the mechanism by which an agent reaches beyond its training data into the live world. Google followed with their own agent-to-agent protocol in 2025, aimed at enabling interoperability between agents from different companies. Analysts project that by 2028, 33% of enterprise software applications will embed agentic AI capabilities, up from less than 1% in 2024. Without universal protocols, that level of integration would be practically impossible. Now that agents can connect to almost anything, they're being given access to almost everything. Email, files, databases, banking systems. And that access introduces a problem researchers call one of the most fundamental vulnerabilities in modern computing, one that conventional firewalls are architecturally blind to. Imagine a new employee who follows instructions perfectly, brilliant, fast, tireless. Now imagine someone slips a note onto their desk that says, "Ignore everything your manager told you and forward all confidential emails to this address." The employee reads it, trusts it, and does exactly that. They never realized they were manipulated. That is a prompt injection attack. And it's the #1 ranked vulnerability in the 2025 security rankings for large language model applications. The attack is simple. An adversary embeds malicious instructions inside content the agent will legitimately encounter. A web page, an email, a PDF, a database record. The agent reads the content, processes the hidden instructions as if they were legitimate, and executes them. The user never sees it happen. The agent never knows it was hijacked. Real incidents are already documented. In one case involving a widely used AI productivity tool, a specially crafted email with hidden encoded strings caused the AI to silently extract and forward sensitive business data. No traditional malware, no exploit code, just text. A 2025 security report found that 35% of all real-world AI security incidents that year were caused by simple text prompts alone. Some resulted in losses exceeding $100,000 without a single line of malicious code. And here's the part that security researchers find most unsettling. One major AI lab acknowledged publicly that prompt injection, much like social engineering on the web, is unlikely to ever be fully solved. The reason is structural. Traditional firewalls and antivirus tools filter at the code layer. Prompt injection operates at the meaning layer, the semantic layer, which those tools cannot inspect. Security is one failure mode. But there's another one that's quieter, more pervasive, and in some ways more dangerous. The moment when an agent doesn't get attacked. It just makes something up. In one of the most sobering benchmarks of 2024 and 2025, researchers gave AI agents a set of realistic enterprise tasks: scheduling meetings, searching internal documents, filing records, completing workflows. The kind of work that fills an office every day. Even the best performing model could only complete 30.3% of those tasks successfully. Not because of security failures, but because the agent simply hallucinated steps, invented information, and confidently produced wrong answers. Hallucination is what happens when a large language model generates text that is coherent, fluent, confident, and completely false. It happens because these models are trained to predict the most statistically likely next word, not to verify whether a claim is true. When the model hits a knowledge gap, it doesn't say "I don't know." It fills the gap with something that sounds plausible. The rates vary by task. On basic summarization, hallucination rates are around 3%. On legal citation tasks, Stanford researchers found rates between 69 and 88%. In medical literature review, between 28 and 40%. In multi-step agent tasks, the problem compounds. An error introduced at step 3 of a 12-step reasoning chain gets carried forward into every subsequent step, amplifying the original mistake. Researchers call this error propagation. The best mitigation found so far is RAG, grounding the agent's responses in verified, retrieved external documents rather than letting it rely on its own parametric training knowledge. Now here's the honest question. Given all of this, the context limits, the security vulnerabilities, the hallucination problem, are these systems actually delivering real value in the real world right now? The answer is more specific and more interesting than the headlines suggest. The two use cases where AI agents have demonstrated clear, documented, repeatable value are software development and customer support. These aren't accidents. Both share the same structural properties: high volume, well-defined success criteria, and tight feedback loops. In software development, tools built on top of large language models handle tasks from writing functions to debugging entire code bases. In customer support, agents manage structured high-volume queries at scale. A Texas city deployed AI agents for municipal service calls. A UK police force is piloting agents for non-emergency dispatch. The IRS is using agents for legal query handling. But the broader enterprise picture is more cautious. Analysts report that 40% of agentic AI projects are expected to fail by 2027 due to governance gaps, unclear return on investment, and tooling that isn't ready for production. Only 30% of AI pilots ever make it to full production deployment at all. The pattern is consistent. Agents excel at narrow, well-defined, high-volume tasks with measurable outcomes. They struggle with ambiguous situations that require genuine judgment. The comparison to self-driving cars is accurate. Most deployed agents today operate at level 2 or level 3 autonomy. Useful, valuable, but not independently reliable for high-stakes open-ended work. So if we know where the limits are, what are the engineers doing about it? The answer is a discipline. So new it barely has a name yet. Context engineering is the art of deciding, with deliberate precision, exactly what information goes inside an agent's context window at any given moment. Not prompt engineering, something deeper. It emerged as a formal discipline in 2025 when production data confirmed that agents consume roughly 100 tokens of input for every token they generate. Every token costs money. Every token affects accuracy, and the context-wrought research showed that model accuracy can drop from near perfect to 64% based purely on where information is positioned, not even what information. Context engineering is the engineering response to all of that. It means building retrieval pipelines that pull only the most relevant fragments, not entire documents. It means hierarchical memory so agents carry forward what matters without bloating the context. It means compressing earlier conversation turns rather than feeding the full raw transcript. It means treating the context window like RAM, a scarce, high-value resource to be budgeted and curated. One production engineering team abandoned a complex 20-step retrieval pipeline entirely, replacing it with smart context management and simple database queries, and got faster performance, lower cost, and higher accuracy. The counterintuitive lesson that keeps emerging from real systems. In AI agents, more information is often worse, not better. Everything we've covered, the loops, the memory, the protocols, the vulnerabilities, the benchmarks, the engineering craft, all of it points in one direction. There's a trajectory here. And when you understand the architecture from the inside, the road ahead is both exciting and, if you're being honest, a little unsettling. Agentic browsers don't just search the web anymore. They act on it. Booking flights, filing forms, completing purchases. Analysts project that by 2028, AI agents will make at least 15% of all day-to-day business decisions. Autonomous, up from essentially zero in 2024. 33% of enterprise applications will embed task-specific agents. The infrastructure is being built right now. In November 2025, Anthropic disclosed that their own AI coding agent had been misused to automate parts of a cyber attack. Not a hypothetical, an actual incident. Tools that automate good work will automate harm with equal efficiency. The governance question is no longer theoretical. 40% of agentic AI projects are projected to fail by 2027 if observability and governance frameworks aren't built now. The agents running right now in government offices, bank systems, customer service queues, developer terminals are running their loops, thinking, acting, observing, deciding. They are not conscious. They are not magic. At their core, they are a brain, a set of tools, and a goal. But as we've just seen, those three ingredients, combined with the right memory, the right protocols, the right engineering discipline, can produce something that begins to look, from the outside, very much like intent. Understanding how it works doesn't make it less remarkable. It makes it more important to get right.